We are calculating the exact ground eigenvalue of the twisted Laplace-Beltrami operator on a Möbius band. This involves finding the fundamental frequency of a field defined on a non-orientable surface with a boundary. The baseline for this problem is a flat Euclidean strip with the metric ds squared equals dy squared plus dw squared. To account for the Möbius twist, we impose an anti-periodic boundary condition. A single traversal along the length of the band returns the function to its negative value. When we solve the standard Laplacian for this strip in the sector where the function is constant across the width, the solutions take the form of a complex exponential, e to the kiy. The boundary loop of this band has a length of 2 pi r, matching the circumference of a reference circle with radius r. This geometric constraint forces the ground state wave number to yield an eigenvalue of exactly 1 over r squared. On a surface with constant Gaussian curvature, the intrinsic scalar curvature, r sigma, is defined as 2 over r squared. The flat geometry produces an eigenvalue that accounts for exactly half of that scalar curvature. This leaves a 50% discrepancy between the flat spectral baseline and the expected curvature of a rounded space. We can resolve this discrepancy by embedding the Möbius strip into a three-dimensional sphere, S3. We place the strip onto an equatorial 2-sphere within that ambient space. This specific embedding is totally geodesic. This means the extrinsic curvature, the way the surface bends relative to the space surrounding it, is 0 at every point. In a totally geodesic embedding, the surface inherits its curvature entirely from the ambient manifold. Any path that is a straight line on the surface is also a straight line in the three-dimensional sphere. Because S3 has a constant Gaussian curvature of 1 over r squared, the embedded strip now carries an intrinsic scalar curvature of 2 over r squared. This inherited ambient curvature doubles the twisted Laplacian's ground eigenvalue. The new value of 2 over r squared now matches the surface scalar curvature exactly. The embedding acts as a direct geometric mechanism to shift the manifold's fundamental spectral frequency without altering its underlying Möbius topology. To verify this shift, we construct the intrinsic metric of the embedded surface using Fermi coordinates. We define w as the arc length along the reference great circle, and y as the meridional arc length extending perpendicularly from that circle. Determined by a Jacobi field calculation, the metric coefficient follows a cosine profile, yielding ds squared equals dy squared plus cosine squared of y over r dw squared. At y equals pi r over 2, the cosine term reaches 0, causing the transverse width to collapse into a single point, creating a singularity. This is the cone point, located at the pole of the totally geodesic sphere. It represents a point where the local coordinate system degenerates. We operate within sector A, restricting our search to functions continuous at the cone point. This allows us to ignore unbounded logarithmic solutions that would make the differential operator undefined. By selecting the regular branch of solutions, we can proceed with the eigenvalue calculation despite the presence of the metric singularity at the pole. We will now establish an upper limit for the ground eigenvalue through a direct calculation. Here is the Laplace-Beltrami operator for our specific metric. The cosine coefficient introduces a tangent term into the differential equation. We test the operator with the ground eigenfunction, sine of y over r, placing its antinode at the cone point. Substituting this into the operator, the derivatives and tangent term algebraically simplify to exactly 2 over r squared times our original test function. This function satisfies the anti-periodic boundary condition, returning its negative value when advanced by pi r. Integrating this wave through the Rayleigh quotient confirms this result, providing a consistent value for the energy of this mode. This calculation sets a rigorous upper bound at 2 over r squared. We proved the eigenvalue can be this low, but we must now determine if it is the absolute floor. To find the absolute lower bound, we apply the two-dimensional Bochner formula, which analyzes the geometry of the gradient independently of any specific test function. The integrated Bochner identity relates the Laplacian of the gradient to the Hessian, the Ricci curvature, and a boundary flux term. To establish a clean bound, we must prove the boundary flux is zero at the outer edges and at the interior cone point. On the outer edges, the totally geodesic embedding ensures the boundaries are geodesics. This means their geodesic curvature is zero, causing the Neumann boundary flux to vanish. We isolate the singularity through epsilon excision, drawing two small boundary curves around the pole. The function's derivative scales linearly with epsilon, causing the total flux to scale as epsilon squared. As the excision zone shrinks to zero, the flux disappears entirely. With all boundary fluxes eliminated, the Bochner formula simplifies into a direct relationship between the eigenvalue and the surface curvature. We apply a trace inequality to the Hessian matrix, establishing that its squared magnitude is at least half the square of the Laplacian. Substituting our inherited curvature of 1 over r squared into this inequality reveals that the eigenvalue lambda must be greater than or equal to 2 over r squared. By mathematically excising the singularity and utilizing the geodesic nature of the boundaries, we have established an absolute spectral floor. The upper and lower bounds have met. The ground eigenvalue is precisely 2 over r squared, which is exactly equal to the surface scalar curvature. For these bounds to meet at an exact equality, the Hessian of the eigenfunction must be perfectly proportional to the surface's metric tensor at every point. Our test function, sine of y over r, satisfies this Hessian condition. The way the function curves across the band perfectly matches the way the manifold itself is curved. This ensures that the ground state is the inevitable geometric result of the space's curvature, locking the spectrum into a specific predictable value. This result mirrors what we see in the closed, smooth, non-orientable surface RP2, which also has a ground eigenvalue equal to its scalar curvature. On RP2, this is a result of global spherical harmonic theory on a manifold with no boundaries. In our model, the Möbius band achieves this same result through a different path, the inheritance of curvature from the totally geodesic S3 embedding. This equivalence depends entirely on the geodesic boundaries and the neutralization of the metric singularity through the conditions of sector A. This demonstrates that totally geodesic embeddings allow singular, open surfaces to maintain the same spectral properties as smooth, closed manifolds.